Hey everyone, and welcome. Today we're going to dive into one of the most fundamental ideas in all of physics, energy. It's what powers everything from a simple light bulb to the entire universe. And figuring out how it's conserved and how we can use it efficiently, that's one of the biggest challenges we face.
So let me kick things off with a question for you. Right now, just sitting there, are you doing work? You might feel like you are, especially if you're trying to study this stuff, but in the world of physics, the answer might actually surprise you.
And the reason why might be surprising is because it all comes down to definitions. You see, everyday words we use all the time, like work, energy, and power, they have these super precise meanings in science. So first up, let's get our definitions straight.
Yeah, in our daily lives, work just means putting in effort, right? Doing homework, going to the gym, that's work. But in physics, the rules are way stricter. Get this. You could push on a solid brick wall with all your might, sweating, getting exhausted. But if that wall doesn't move one single inch, you've technically done zero work. Crazy, right?
So for work to actually happen in a physics sense, you need two things, and they're non-negotiable. You need a force, and you need movement, what we call displacement in the same direction as that force. The formula is pretty straightforward. Work is just the force you apply times the distance you move it. No movement, no work. It's a direct measure of that force being applied over a distance.
Okay, so if work is the action, then what's energy? Well, you can think of energy as simply the potential to do that work. It's the juice in the tank. It's the property that a system has that allows it to perform work. They're really just two sides of the same coin, and we even measure them in the same unit, joules.
And this deep connection between work and energy leads us straight to one of the most profound, one of the most unbreakable laws in the entire universe. This is a rule that governs every single thing that happens, from tiny atoms to massive galaxies.
And here it is, the principle of conservation of energy. It's an absolute law. It means that in any closed system, and that's a system where no energy gets in or out, the total amount of energy inside stays exactly the same, always. You can't just make new energy out of thin air, and you can't make it vanish. All you can do is change its disguise.
Here's a really cool way to wrap your head around it. Just imagine that the universe started with a fixed energy budget, a set amount. Everything that's happened since the Big Bang is just that initial energy being shuffled around, moved, and converted from one form to another. The grand total has never, ever changed.
And this conversion is happening all around us, all the time. Take a battery, for instance. It's just packed with stored chemical energy, right? Well, you connect it to a lamp, and that chemical energy converts into electrical energy flowing through the wires. Then that electrical energy transforms into light, which is what we want, and also heat radiating from the bulb. See? The energy wasn't created, it just changed form, step by step.
Okay, but this brings up a really great question, doesn't it? If energy is always conserved, if it never really disappears, then why is everyone always telling us to save energy? What are we actually saving it from? Well, this is where the absolutely crucial idea of efficiency comes into play. Let's go back to that light bulb. When you flip the switch, what do you want it to do? You want light, obviously. But as we just saw, it also makes heat. So, which kind of bulb is better at giving you what you actually want?
Well, the difference is just staggering. An old-school filament lamp might turn only 5% of its electrical energy into useful light. That means the other 95% is just wasted as heat. But a modern LED, it's way more efficient, maybe turning 50% into light. Now, in both cases, the total energy is conserved, sure, but the LED gives us 10 times more of the thing we actually want. That is what saving energy is all about, trying to minimize the useless stuff that gets produced along the way.
So the formal definition of efficiency is just that simple ratio. It's the useful energy you get out of a machine divided by the total energy you put in, and we usually show it as a percentage. A perfectly 100% efficient machine is impossible, because some energy is almost always lost to heat from friction or other things, which, by the way, is why perpetual motion machines can't exist. The only thing that comes close is maybe an electric heater, because its entire job is to turn electricity into heat.
All right, enough theory. Let's put this stuff into action. We're going to see how these definitions for work, energy, and efficiency aren't just abstract ideas. They let us calculate exactly what's going on in the real world.
First, we need one more key definition, power. So if energy is the ability to do work, power is all about how fast you do that work. It's not just about being able to lift a heavy box. It's about how quickly you can do it. The formula is power equals the work done divided by the time it took. And the unit for that is the watt.
which is just 1 joule of energy used every second.
Okay, let's watch how all this comes together in a real calculation. Let's say we've got a motor lifting a weight. First, we figure out the work it did. That's force times distance, so 1.5 newtons times 1.2 meters, which gives us 1.8 joules. Easy enough. Now to get the power, we just divide that work by the time it took. So 1.8 joules divided by 2.7 seconds gives us a power output of 0.67 watts. See? It's just a clean, step-by-step process.
All right, let's tackle an efficiency calculation. This is a classic physics problem right here, a pulley system. Our goal is to figure out how much of the effort the guy puts in actually goes into the useful task of lifting that weight.
First things first, let's calculate the total energy the man puts in. We know he pulls with a force of 200 newtons, and he pulls 10.5 meters of rope. So force times distance, that gives us a total work input of 2,100 joules.
Now, what about the useful work that came out of the system? Well, the weight was 480 newtons, and it was lifted 3.5 meters. That means the useful output is 1,680 joules. And you can see right there, it's less than what he put in. The rest of that energy was lost, probably as heat from friction in the pulleys.
So, to find the efficiency, we just divide the useful output by the total input, 1680 divided by 2100, and there's our answer. This pulley system is 80% efficient. That means 20% of the man's effort was just lost to friction.
But look, these calculations aren't just problems in a textbook. This fundamental understanding of energy, power, and efficiency is absolutely critical for tackling the biggest challenges we're facing as a civilization.
And this really gets to the heart of it all. We've defined our terms, we know the laws, so why does this stuff matter so much on a global scale? Why is it so important that we look beyond the fossil fuels that, built the modern world?
Well, the answer really has two huge parts. First, when we convert the chemical energy in fossil fuels into useful work, it also releases greenhouse gases, which has a massive impact on our climate. And second, those resources are finite. They will run out. So for our own long-term energy security, we have to harness other forms of energy that are renewable, like solar, geothermal, or tidal power. And this all brings us to a final, really big thought. We know from the laws of physics that some energy will always be wasted in any conversion. No machine can ever be perfectly efficient. So the challenge for our future is really twofold. How do we find enough clean, primary energy sources? And how do we design systems that are as incredibly efficient as possible to make the absolute most of what we have? The answer to that is going to define the world we live in.